Why do scientists seem to obsess about experimental uncertainty or error? Incidentally, I prefer the term uncertainty because error always sounds to me like a mistake, and this has nothing to do with making mistakes. So what's the point of uncertainty? The only real reason for experimental uncertainty is that it allows us to make a meaningful comparison between our own quantitative experimental measurements and a theoretical model or calculation or someone else's results. Experimental uncertainty tries to quantify the precision or reproducibility of a measurement. Let's consider first an individual measurement. In a titration, you're typically told to measure the volume in a burette to within 1/100th of a milliliter. That is, to read the volume at the bottom of the meniscus to 1/10 of the smallest increment marked on the glass. To achieve this, you must place your eye at the same level as the meniscus and eliminate parallax error. For the image shown, most people would read this as 25.68 milliliters. This means we'd be confident that it isn't 25.69 milliliters or 25.67 milliliters. It also means that we aren't confident about that next decimal place. We can express our experimental uncertainty as a confidence limit, that is 25.68 plus or minus 0.005 mLs, because if it was more than 25.685, we'd read it as 25.69 mLs, and if it was less than 25.675, we'd read it as 25.67. If you're inexperienced or a pessimist, you might have slightly wider error bounds and you might prefer to write 25.68 plus or minus 0.01 mLs. In an actual titration, you measure the titer as a difference between initial and final volumes. So let's suppose these values are 25.68 plus or minus 0.005 and 42.43 plus or minus 0.005. So the volume of the titer is the difference, 42.43 minus 25.68, that's 16.75 mLs. But what's the uncertainty? The smallest the titer could be is 42.425 minus 25.685 or 16.74 mLs, and the largest it could be is 16.76 mLs. But these limits are only reached if the errors combine in the worst possible way. As the initial and final volumes are independent measurements, we should combine their uncertainties as statistically independent probabilities. If you like, that's a vector sum. So the uncertainty sigma for the titer is equal to the uncertainty in the initial volume squared plus the uncertainty in the final volume squared, all taken to the power 1/2. If we carry that calculation through, we get a total error of 0.007 milliliters. So you can write this titer as 16.75 plus or minus 0.007 mLs. And if you were more pessimistic when you started, you'd end up with 16.75 plus or minus 0.014 mLs for your titer and uncertainty. The uncertainty in the titer is greater than that for a single burette reading, but not as bad as the worst case scenario, because we don't know whether the errors add or cancel. Now let's compare 4 titration values shown in this table. I've got 4 samples, 4 titration volumes, 16.75, 16.74, 16.79 and 16.76 mLs. These all look the same, but sample 3 is clearly outside the range expected for reproducible results. This is easily seen by comparing results graphically with our uncertainty for each measurement shown as error bars. The coloured band illustrates how the error bars of the measurements on samples 1, 2 and 4 overlap, but sample 3 does not. Now either something went wrong with that titration, or there's something genuinely different about that sample. We don't have enough information to draw any further conclusions, but I'd certainly look more closely at sample 3. Now imagine that sample 3 was a mistake. Maybe you left the funnel in top of the burette for that one. Samples 1, 2 and 4 represent the reproducibility of a single titration without any mistakes. So our final titer is the average of these 3 good results, 16.75 mLs. But what's the uncertainty now? The real question here is, do we use the statistical uncertainty of the mean, or do we have to build in the uncertainty of each measurement somehow? The point of doing multiple measurements, each with a random uncertainty, is to get closer and closer to the real or reproducible value. The uncertainties on each measurement were our best guess at how precise or reproducible a single measurement could be. But by reproducing the measurements, we have actual data on their reproducibility. For 5 or more good measurements, we use standard deviation. For fewer, we use the maximum deviation from the mean. Here, that would be 0.01 mLs, and our answer is 16.75 plus or minus 0.01 mLs. As you took more and more measurements, you'd expect the uncertainty, the standard deviation, to get progressively smaller. Statistically, this decreases in proportion to the square root of the number of measurements. So the standard deviation of n measurements of a quantity x is given by the formula shown. Rarely would we repeat a single measurement like a titration enough times to care about the standard deviation. However, we often make measurements of a dependent variable as a function of independent variable and fit it to a straight line or other function. Suppose we were to measure conductivity as a function of concentration. Each of those conductivity measurements has an associated uncertainty. If we fit the data to a straight line, then that line has a slope and an intercept, and they also have associated uncertainties. And just as we saw with averaging, the data, which we've assumed to be described by the equation given, is scattered about that line. This gives us information about the reproducibility or uncertainty of our measurement. We can use the standard deviation of the slope and intercept of a line of best fit to determine uncertainty. Programs like Excel will determine this for you in their data analysis tools. Don't just use the R² value from a fit or a trend line to describe how well your data is fed by your equation. So a line of best fit to an equation like y equals mx plus b with a slope m and an intercept b for the data shown would be given by m equals 0.493 plus or minus 0.010 and b equals 1.021 plus or minus 0.035. Now actually, when I used Excel to fit y equals mx plus b to that data, it gave me back m equals 0.49285714285743 plus or minus 0.00984574910863586 and something similar for beta. So how do you decide how to round off? For m, you just can't round off the uncertainty to 0.0098. As noted in the lab manual appendix on data handling, normally enough digits should be given so that the last one to the right is largely uncertain, usually by more than 3, and the next to last is slightly uncertain, by less than 3. The number of digits in the uncertainty should be given such that the limit of error lies in the range 03 to 30 in the last 2 digits. 98 lies outside that range. You need to round off to 0.010. That then determines the number of meaningful decimal places in the actual quantity m, which must be the same for the quantity and the uncertainty. So we round it off to m equals 0.493 plus or minus 0.010. You do the same for b and for all such